YA and YB are made from the same material. YB has 3 times the diameter and twice the length. The resistive wire A is ρ. What is the resistivity of wire B? Okay, what some students might do in this case is take the equation for resistivity, and they might realize that area is directly proportional to the diameter squared. So if the 3 gets squared, it becomes times 9. So they'll say, okay, well, the area has become times 9, and they'll realize that the length is times 2. And then, as you can see, one of the options given to us is 9 over 2 over here. So they might go for that answer there. Okay, however, this is incorrect. The reason is because of this statement here. It's the same material, and they're asking us to compare the resistivity. Okay, so that means the resistivity should be the same for both wires because it's the same material. Because resistivity only depends on the material that you're choosing, and also a bit of temperature as well. So the answer here is actually A. Now in this question they're asking us to compare the resistance. Resistance of wire A is R. What is the resistance of wire B? Okay, now this is when I get the equation for resistance like this. I know that the same material, so I can ignore ρ. It's going to be the same for both. The length is times 2. The area is going to be times 9 because of the square. So the answer here is going to be 2 over 9R. And that makes sense. If you made the length longer, the resistance should go up. However, you've made the area much bigger, so the resistance should go down. Overall, the effect is for the resistance to go down. The silver wire of length L and diameter D has a resistance of 50 ohms. What is the resistance of a silver wire which has twice the length and half the diameter? Okay, still a silver wire here, so that means the resistivity is going to be the same. So if I write the equation for resistance, I can ignore resistivity, it's the same material. The length is going to be times 2, okay, and the diameter is going to be a half. Now, because the diameter is being halved and the area is proportional to diameter squared, that's going to get squared. So that's actually times a quarter at the bottom. Now, because it's a fraction, all you have to do is flip over, and you're divided by a fraction, you flip it over and multiply. So 2 at the top times 4 over 1, which is just the same as times 4, that gives me times 8. So overall effect on the resistance will be 8 times larger. That makes sense because we made it longer, which is going to make it harder for the current to flow through, and also we've narrowed it as well. So that's also going to make it harder for the current to flow through, increasing the resistance. Okay, when a constant potential difference is applied across the ends of a uniform wire, there is current I in the wire. The wire is replaced by one made from the same material. That means the resistivity is constant, but the triple the length and double the diameter. Okay, the same potential difference applied across the new wire. What is a new current? Okay, so we're going to figure out what happens to the resistance of this new wire compared to the old one. So resistivity is going to be constant, so I can ignore that. The length is going to be 3 times. The area, we know is going to be times 2 squared, so it's going to be times 4. So resistance is going to be times 3 over 4. Okay, what effect is it going to have on the current? So we can use Ohm's law. V equals IR, and I'm going to rearrange this to get I as a subject, so V equals I equals V over R. V is constant, it tells us the same potential difference, so I can ignore this. It's inverse proportional current is inverse. So if this is times 3 over 4, because of the bottom is going to get flipped over, the current is going to be 4 over 3 of the initial amount. Okay, it's 4 over 3I. So that's the final answer there. Okay, alternatively, I could have done all of this in one go. I could have written resistance in terms of resistivity, length, and area, and substituted Ohm's law, and then rearranged this. I could have done it like this, and I would have gotten the same answer. The resistance of a wire is measured to be R. It is stretched to double its length. The total volume remains constant as it stretches. What is the new resistance of the wire? Okay. So I know the length is going to be double, but I'm not quite sure what's going to happen to the area. But however, I do know the volume is constant. The volume for a wire like this is going to be the cross-section area times the length. And because I don't know how this A is going to change, I'm going to eliminate this A using this equation here. So let's make A the subject. So V over L equals A. And if I put it into this equation here, I get resistance equals resistivity length over volume over length. When you divide by a fraction, you simply flip it over and multiply. So that becomes resistivity length times length over volume. And that expands to give you resistivity length squared over volume. Okay, now I know it's the same material, so that means I can ignore the resistivity. I know the volume is constant, so I can ignore that as well. So it turns out resistance is going to be proportional to length squared. The length is being doubled, so that gets squared as well. So the resistance is going to actually be times 4.